Hi everyone, welcome to your first lecture. These lectures are going to be a little bit compressed. I'll probably try and provide a video lecture once a week, which is a lot less than we would normally have if we were taking a face-to-face course. But you have a lot of resources available. You have the PowerPoint slides available online. There will also be lectures from Walter Lewin. They're from the early aughts, but they're from MIT, and I think they're excellent learning materials. And then, of course, you have your textbook. So let's go through waves and wave motion. And I'm going to skip through these first couple slides in here. These are for you to read on your own, learning outcomes and stuff like that. And let's just talk about what a wave is. A wave is a disturbance in a medium that transports energy from one place to another a long distance, even though the medium itself doesn't move very much, right? So you can think about water not moving a significant amount, the water molecules, although the energy of the wave can be transported across an ocean or across a lake, okay? So there's two types of this wave motion. There's a longitudinal wave. This would be like waves in a slinky or a spring, or also sound waves. And a longitudinal wave, the material, the medium, moves parallel to the direction that the energy propagates. Another type of wave is a transverse wave, and this is where the medium or the material moves in a direction which is perpendicular to the direction the energy propagates. Okay, examples of this would be light, electromagnetic radiation, and waves on a guitar string or a piano string. Water waves are a little bit more complicated. They have both transverse and longitudinal components, and that's because the water moves in a circular fashion as the wave propagates through. You can imagine just watching a duck on a lake, and as a wave from a passing boat comes by, the duck moves forward and down and back and up. And its motion is a circle as the wave propagates by. Okay, so moving on to some properties of waves. A wave is a function of two independent variables. A transverse wave, for example, a wave on a guitar string, for example, the height of the string depends on both the position along the string as well as the time that you're making that measurement. So two independent variables. This is unlike what most of the things we've been doing in Physics 1. Okay, so you're familiar with simple harmonic motion. That was something we talked about in Physics 1. Simple harmonic oscillator, we can have y of t, that's a function of a singular variable, is some amplitude times cosine of some angular frequency omega t, and depending on the initial conditions we have some phase angle phi. Okay? So remember from simple harmonic motion that the period t and y. That's not a very good drawing. The period is the time it takes to go through one complete cycle of the wave. So this is t, and the angular frequency, this term right here, is 2 pi divided by t. Okay, that's the angular frequency, and units are radians per second. Okay, so let's now look at a wave as a bunch of independent simple harmonic oscillators. You can think about this as maybe I have a bunch of masses on springs. This, and they're all oscillating up and down but they're all out of phase from each other. It's as if they were connected by strings, and one mass feels the effect of the first mass and responds a little bit after the first mass has already started its motion. So we can view this as a set of an infinite set of simple harmonic oscillators. Okay? If we think about it that way, then if we want to know what the motion's like somewhere down the road in space, right? So here's, let's say that this is at x equals 0. And now we'll say over here we've got some other simple harmonic motion at x equals 1 centimeter. But this one is shifted over. So notice that the peak over here is at x equals 0. At x equals 1 centimeter, the peak, the amplitude right here, is at its maximum at some time delta t, which is not at t equals 0, right? So this is simple harmonic motion just like this one. The period is the same. Period is also from peak to peak, right? But the motion begins at some time later down the road, okay? So let's take a look at some other properties of waves, right? Waves travel at a speed which is entirely dependent on the medium that they travel through. And so if the medium, the material, doesn't change, then the wave speed doesn't change. And the wave speed is given by the wavelength, lambda, divided by t, which we can also write as the wavelength times the frequency, since frequency is the reciprocal of the period. Okay? So, if I want my wave motion to start, let's say y of x equals 0 t is a cosine omega t, then y x equals some other x prime, we'll call it t, should be a cosine omega times, I should replace this t with something else. So let's put it as, let's call it t plus some other parameter, some delta t or something like that. Delta t. Okay? And if I want this to start later, what I've done is I've taken this graph and I've shifted it to the right. So if I want to shift that to the right, I need to put a minus sign in here. Okay? Okay, so what should delta t be for this motion to start later if the wave energy is propagating at this velocity? Well, since this velocity is constant, right, then I have delta t is x, in this case we'll say x prime, divided by delta v. Okay? So, if I want to put this in here, start at the top. I get y of x equals x prime, and t is a cosine omega times t minus x prime over v. I don't know why I wrote a delta v down here. That's not right. That should have been just x prime over v. All right. Okay, so let's do some other little tricks. First thing is just to recognize that cosine is an even function. So if I multiply the argument by -1 I don't really change anything. So we can do that. Let's write this as omega times x prime divided by b minus t. Okay, so we just multiplied the argument by -1. Next thing is omega is 2 pi over t, and we have v is lambda divided by t. So let's plug those in. I get y, y is a function of x equals x prime, and t is a cosine, right, this is omega is 2 pi over t, and then we'll write x prime over 2 pi, over lambda over t, x prime over lambda times t minus lowercase t. Okay, so we've got our simple harmonic motion at this point x prime. Let's just say we're talking about any x. So we'll just get rid of the prime and say, what is y as a function of x and t? Y as a function of x and t is a cosine. Let's see. I've got 2 pi. The t's cancel in this first term. I'm going to distribute this to both terms. So I've got 2 pi x over lambda minus 2 pi over t times t. Alright, so now I'm getting somewhere. I've got a wave function. Alright, and we'll define these things. We already know 2 pi over t, that is what we call the angular frequency omega. Let's define this term over here, and we'll call this term k, and that is wave number, is what we'll call that. Wave number. And it has units of radians per meter, not radians per second, but radians per meter. Okay? Once we've done that, we can rewrite our equation as y of x and t is a cosine kx minus omega t. Okay? All right, so which way is this wave traveling? It's traveling to the right because there's a minus sign here. If we wanted to make the wave travel instead to the left, we would have to replace that with a plus sign. Okay? We shifted it so that the simple harmonic motion at a point along the positive x-axis occurred later than at x equals 0. There's another way we can look at this too. We can look at this in terms of the wave as a snapshot. So we can imagine at one instant in time, let's say t equals 0, we have a graph which shows the wave. And this is y as a function of x. Okay? So this no longer represents the period. This is the wavelength. Okay? And that means if we want at some time later to see what this wave looks like, let's say t equals t prime, and we have something that looks like, forgive my horrible drawings, this, and there's some shift here, right? Some shift that happens there, and so we could think of this as now y as a function of x at t equals 0 is a cosine k times x. And if I want to shift this to the right, then I have y x and t equals a cosine k times x plus delta x. If I want to shift it to the right, then this has to be a minus sign. If I wanted to shift it to the left, it would be a plus sign, right? Just from what you know about algebra and shifting functions. Okay, so what is delta x now? It's v times t, which is lambda over t times t. Okay, but k is 2 pi over lambda. So v and omega, I should write, is 2 pi over t. So we can also write v is omega over k. Right, angular frequency divided by the wave number. So that gives us y of x and t is a cosine kx minus, if I've distributed this k over to here, I have k times lambda divided by t. That would be 2 pi over t. Oh, that's just omega minus omega t. So you can think of it as we shifted the function, a snapshot, a picture of the wave, over in space as a function of time, or you can think about it as we have simple harmonic motion at one point, and then that same simple harmonic motion repeats itself at a different point in space, but sometime later. Right? Either way, we get the same wave function. Okay. All right. Skipping through these, I'll let you go through those. Now, anything could be a wave. Any function could be a wave as long as it meets some certain criteria. One thing to think about is, could y equals 1/3 x be a wave? Well, no. Y is just a function of x. And in that case, it's a straight line that goes through the origin, like this, with a slope of 1/3. But if this line, for example, moves so that at some time later, it's over here, and it moves at a constant speed v, we could write this as y of x and t is 1/3. Now I have to replace my x here with x minus, and then delta x would be v times t. This could be a wave, right? It's got an argument x minus vt here. And if I have something that has a form y of x and t is some function of kx minus omega t, then it will be a wave. It'll always be a wave, no matter what that function is. Okay, but there are other things, other functions that could also be waves. For example, if I take a bunch of cosine functions and I add them together, I could do some trig and get something that looks completely unlike the wave function that we had in the last slide here. But that doesn't mean it's not necessarily a wave. So how can we determine what is a wave and what isn't a wave? Waves obey a simple differential equation, partial differential equation called the wave equation. And what that says, the wave equation says that the second derivative of y with respect to x is proportional to the second derivative of y with respect to t. And the constant of proportionality is 1 over the velocity squared. Okay, so remember, let's remind you what partial derivatives are. dy dx, and these are little script d's, they're not 2's, just means take dy dx, treating t as a constant. Okay, so for example, is this a wave? Sine kx sine omega t. Well, let's try it. Okay, we take the derivative of y with respect to x, treating t as a constant. So that means this whole term is just a constant term. Sine omega t is constant. So when I take the derivative with respect to x here, I get derivative of sine is cosine. So I have cosine kx times k from the chain rule, right? Derivative of kx is k, times sine omega t. Now I take the second derivative. Derivative of cosine is minus sine, so I get minus chain rule, I get k squared sine of kx sine omega t. Alright, now let's do the derivatives with respect to t. dy dt, alright, this we could recognize as the velocity of the material in the up and down direction. Right? You can think of this term, this is the slope of a string at some point. If this is a wave, by the way. This one would be the curvature or concavity. All right. Now this one will be the velocity. Let's write that over here. Vy, it's the y component of the velocity, not the wave's velocity, but the velocity of the material in the up and down direction, if this is a wave. So we take the derivative with respect to t, and what do I get? Now I've got sine kx, that's just a constant. But now I've got cosine omega t, and then I do the chain rule, I get an omega when I take the derivative with respect to t. We're treating x as a constant. Now the acceleration in the y direction, right, if this is a wave, is the second derivative of y with respect to t. Now I take a second derivative and I get minus sine kx times sine omega t times omega squared from the chain rule. Okay, we can put this together. If this satisfies the wave equation, if the velocity squared is equal to the second derivative of y with respect to t over the second derivative of y with respect to x. And when we do that, we see that the signs and the signs in these equations cancel out. The minus sign in front cancels out, and what we're left with is omega squared over k squared, which we know is the velocity of a wave. So this is a wave. Okay, so now thinking about a wave on a string, how does what properties of the material does the wave speed depend on? Okay, and a simple example of this is to use Newton's second law together with the wave equation. Okay, so if we're doing that, in this example we have a little tiny piece of the string of length delta x. And the linear mass density of the string, call that mu, right? Mu is the mass of the string divided by its length. It's linear density, not volumetric density. And that means that this will also be true if this is uniform. It will be, let's call it dm over dx, right? Some very small bit of the string will also be equal to that. So you can see in the figure up in the upper right that we have forces that are pulling on the string, and those forces are due to the motion of the string, so the other piece is pulling on it in the up and down direction, and also to the string tension, right? That's how tight the string is tightened. Call that T. So the x component of the force is the tension, and the y component of the force is, well, it depends on the neighboring parts of the string pulling on it. So we don't know what, at the ends of this little bit of string, what the y components of the force are, but we do know the x components. They're just the tension in the string. Okay, so if we want to know what the y components are, we can use the x component times tangent theta gives us the y component, and tangent theta is the defined as y over x, right? It's the the opposite side of the triangle divided by the adjacent side of the triangle. And so for these force vectors, this is the slope, right? And we can write that as dy dx at x and dy dx at x plus delta x. Okay, so those are the slopes. Let's write that as slope at x, and this is slope at x plus delta x. Okay, so now we can look at the difference in the y components of the forces. Right, that will be the x component of the force, T, times, now I need tangent of theta 2, that is on the F2 side. That turns out to be the slope of the string. The force, the net force, is tangent to the string itself. And the string is kind of in an upward direction at that point. So we have a slope dy dx at x plus delta x. Then we need to subtract off the force at the beginning of that section of string, F1y, which is t again, minus the slope there, which is dy dx at x. Now Newton's second law says this is F net on this section of the string, and this should be equal to ma, and this is the y component, F net y. This is m-a-y. But we can write this m as the linear density times the length. Okay, and we can write the a as the second derivative of y with respect to t. Okay, once we do this, if we divide through by delta x and divide through by t on both sides, then we get dy dx at x plus delta x minus dy dx at x divided by delta x is mu over t times second derivative of y with respect to t. Okay, now all we have to do is let's take the limit as delta x goes to 0. And you'll recognize that this looks something like the definition of a derivative, except our function is this thing. We'll call this f of x. F of x is the derivative of y with respect to x. So if I take the derivative, this is the definition of the derivative, then this must be the second derivative. Okay? So what we've got here is an equation that says the second derivative of y with respect to x is equal to mu over t times the second derivative of y with respect to t. Hey, that's almost the wave equation as long as this is 1 over v squared. So that tells us v has got to be the tension in the string divided by the linear mass density and then take the square root. So those are the two properties of the string medium on which the velocity depends. That's the velocity of the propagation of energy, not the up and down velocity of any bit of the string, which is given by the derivative of y with respect to t. Okay, I'll let you prove to yourself that the average power in the string is given by 1/2 mu times omega squared a squared v. You can do this just by simple integration. All right. If we have waves like sound waves or light waves that propagate in 3 dimensions, then the amount of power per unit area stays the same. It doesn't change, right? Energy is conserved, and if that energy is not going anywhere else, it stays in that wave. But if the wave spreads to be over a bigger cross-sectional area, that means that the intensity has to go down as we get further away from the source, because the same amount of energy per unit time is spread out over a larger spherical surface area. Surface area of a sphere is 4 pi r squared. Okay, so that means that the intensity decreases with the square of your distance from the source. Okay, I'll let you go through these. For your lab, it's important to know how sound waves velocity depends on the medium. And in an ideal gas, this depends on the pressure, the density, and a factor that's called the ratio of heat capacities, gamma, which is the heat capacity at constant pressure divided by the heat capacity at constant volume. Right. Okay, let's talk about the decibel level. Sound intensity level measured in decibels, we'll call that beta, is not the intensity that you hear or experience in watts per square meter. That's what we'll call I, right? So I is measured in watts per square meter, but because we experience, for example, sound over such a wide range of different intensities, orders of magnitude, we like to reduce that to put them on a scale that just covers a few hundred instead of many, many orders of magnitude. So what we do, we'll say that a bell is log of log base 10 of some intensity divided by some reference intensity level. And a decibel will be 10 log of I over that reference level. And we'll take as a reference I naught to be 10 to the minus 12 watts per square meter. That's the threshold of human hearing. About. Okay. So, moving forward, waves can interfere with each other, and the wave functions of two waves add algebraically point by point in space and in time. So if two waves are on top of each other and the amplitude of both is positive, then the two waves will constructively interfere. The amplitude will be their sum. If two waves overlap each other at some point in space and at some point in time, and one has a positive amplitude and the other one has a negative value amplitude at that point, then the waves will cancel out. That's what we call destructive interference, and the amplitude of the resultant wave will be the difference. Okay. A good example of this is setting up a speaker system. There will be places where you hear constructive interference and places where you hear destructive interference. Let's say that you're in a band and you are mixing down an album and you're using studio reference monitors, which are like these. They're designed for one listener at a point on an equilateral triangle centered between the speakers. Now, something that's going to happen is if you're listening, you're experiencing constructive interference. You are the same distance away from each of the two speakers, right? And so the two waves will add together and you will hear a louder amplitude there. And this is just for monophonic. We're not even considering stereo sound here, but it works the same way. Now, your friend is listening, and your friend is sitting over to your right, okay? But now that your friend is over to your right at point Q, the distance from the right speaker to them is much shorter than the distance from the left speaker to them. And that difference will be exactly half a wavelength for some particular sound. And that means that there'll be destructive interference. The two sound waves will be reaching them out of phase by half of a wavelength, and they will not hear that frequency. So if you're listening to the same song, you'll hear something, you'll say, this sounds great. And your friend, depending on where they're sitting, might say, there's not enough bass in this song. I don't hear it. And that's just a fact of where they're sitting, right? Because they're experiencing destructive interference for some particular frequencies. Okay, so something you'll definitely be going over in your future courses as an engineer or as a physicist, or I don't know what all your majors are, but you'll be learning about most likely Fourier analysis. Joseph Fourier showed that any periodic function can be written as an infinite sum of sine and cosine functions, simple harmonic functions. So what about different sounds? One example is a clarinet. A clarinet kind of has this weird kind of buzzy sound. Not really buzzy, I don't know how to describe it, hollow sound maybe. That's slightly different from the sound of a recorder or a guitar. Why do those sound different? And the difference is not necessarily the pitch that they're playing, right? The frequency of the guitar or the recorder or the clarinet could all be the same. That's the fundamental frequency of the sound waves that they're producing. But the overtones or harmonics, which are added on top of them, change the character of the sound. So for example, if we want to get a square-shaped wave, we add up a bunch of sine waves with different frequencies and different amplitudes, and that will produce this square wave shape. Those are what give the sound of a clarinet versus the sound of a guitar playing the same pitch. Also, if you have waves that are just slightly almost the same frequency but just off by a tiny bit, then there will be the phase differences between them will cause them to oscillate between constructive interference and destructive interference. This is what we call beats, right? So two notes that are very similar in pitch will appear to get louder and quieter with a slow frequency, which is the difference in their two frequencies. The beat frequency is the absolute value of the difference in the frequency of the two waves. Okay. Let's skip through that and go to wave reflection. If I have a string and I initiate a pulse on that string, if the end of the string is fixed, for example, it's glued to a wall, then the wave pulse will reflect back inverted, upside down. Okay. If the end of the string is free to move, like the end of a whip, then when the pulse reaches this free end, it will reflect back right side up. Another way to think about this is if a string were tied to a more dense string being like the wall, which has infinite density, infinite mass, then the wave will reflect back upside down. The transmitted wave, the portion of the wave that goes through the more dense string, will be transmitted right side up, okay, or in phase. Okay. So we can take a look at standing waves now. Standing wave is what happens when a wave reflects off a boundary and comes back, but there's properties of the wave which depend on, where I am in space and where I am in time. So these waves appear to not move, right? That's why they're called standing waves. But there are points in space where there's a lot of oscillation, and other points in space where there is zero oscillation, and those are called nodes. So we can look at a simple example of a string. And on the string, we have a wave which is propagating to the right. Right, so say there's some device here, a mechanical motor or something, which vibrates the string up and down. The wave propagates to the right, and then it reaches a boundary, and the wave reflects back upside down. So where the motor is, we'll have a lot of oscillation. Right? We have a wave that's traveling to the right, and this is a snapshot at one time, but then that wave is reflected back upside down, and the wavelength and period are the same. And so if I looked at strobe light views of this, I would see that the wave would oscillate between these two maxima and minima. Like so. But that oscillation would only occur at certain points. Those are called antinodes. But that there is no oscillation at these other points, which are nodes. Okay, so how do we do this? We have y1 of x and t is a cosine kx minus omega t. That's a wave function for a traveling wave which is propagating to the right. Now I also have the wave which is propagating to the left, and it's upside down, it's inverted. So y2 of x and t will be minus, it's inverted, a cosine kx, but it's also traveling to the left. So I need to change that minus sign to a plus sign, omega t. Okay? If I sum these two, I get a standing wave. And with a little bit of trigonometry, what you'll find is this gives us 2a sine kx sine omega t. And you can go through that trig on your own. But what you'll see is, where are the nodes? Nodes are where x equals 2 pi, or let's say n pi, over k, right? So let's make sure I said that right. If sine of 0 or pi is 0, sine of pi over 2 or 3 pi over 2 is 1 or minus 1. So as long as n is an integer, 1, 2, 3, 4, 5, then n pi, or nx over k will give me, let's see, oh, that should be n pi x over k, sorry. N pi x over k will give me 0 here. And we can see this is our simple harmonic motion at a point. But this is where I am along the string. And this will be x equals 0 over here. So that means that the amplitude will be 0 at any time t at these points, which we call nodes. All right. In musical instruments, in, for example, a column of air, we can have standing waves as well. If I have a tube, like a pipe organ tube, that is closed at one end, then that must be a minimum for the wave. Sound waves are longitudinal, and if there's a wall or a barrier, then the air can no longer move parallel to the direction of propagation. So that must be a node. Okay? If instead both ends are open, that's like a free end of the string, and the amplitude of oscillation will be maximum at both ends. So the ends will be an antinode, like case B, if both ends are open. Okay. Last topic I think we have for today is the Doppler effect, which is what happens if the source of waves is moving. And remember that wave speed travels, the speed of waves depends only on the medium. So even motion of the source of waves will not cause the speed to change. Instead, what gives are the frequency and the wavelength that an observer would hear relative to the frequency and that the source was emitting. So let's first consider the case where there's a source and it's moving relative to a listener, okay? And it's moving away from the listener. We'll treat that as the positive x direction. And what we can see is that because the wave speed is the same, even though the source is moving, the wavelength in front of the listener is compressed, and the wavelength behind the listener is stretched out. So an observer, here's a frequency, listener, F observer, is the velocity divided by this new wavelength. We'll call it lambda prime, the lambda behind them. Well, the wavelength is different by v plus the velocity of the source divided by the frequency of the source. Okay, so that means that the observer hears a frequency which is smaller than the frequency of the source. It's a lower pitch. Right? So as the source moves away, the pitch of the sound, or the frequency of the light, or whatever kind of wave it is smaller for the observer than it was for the source. Okay, but now let's consider the case where the source is at rest and the listener moves towards the source. Now, the wavelength that the source is emitting is the same in all directions, But the source, the listener, the observer, will encounter the peaks of the waves more frequently as they move into the incoming waves. So now the frequency the observer hears will be the velocity plus the velocity of the observer divided by the velocity of sound, right? V is the velocity of sound times the frequency of the source. So if we put these two together, we get that the frequency of the observer hears, in either case, is the velocity of sound, or the velocity of waves, plus or minus the velocity of the observer, divided by the velocity of sound, or whatever waves we're talking about, plus or minus the velocity of the source, times the frequency of the source. And all we did was combine both features of the two examples into one function. Now, something to keep in mind here, this is the case where the observer is behind the source, and both the observer and the source are moving in the positive x direction. Okay? What that means is that this formula is only true if the observer is moving toward, I'm sorry, not true. The formula is, these are both positive signs, if the observer is moving towards the source and the source is moving away from the listener. If the source were moving towards the observer, the listener, then this would be a minus sign. If the observer or listener was moving away from the source, then this would be a minus sign. Okay, so what is this Doppler effect? This is the familiar car goes by. When it's approaching you, you hear a higher pitch. When it's receding away from you, you hear a lower pitch. So the sound of sitting on the side of a road, listening to a car go by is, that's the Doppler effect. Okay. We also have the Doppler effect for light, but since light is a very special wave, it doesn't travel through a particular medium. What we'll learn throughout most of this course is that light travels through the electromagnetic field. But the electromagnetic field is sort of a construct that we make up, or it's, I mean, you could think of it that way. Because of that, there is no still air in the case of sound that is a reference point for the velocity of both the listener and the source. In that case, we only have one velocity. It's the relative velocity between the source and the observer, right? I'm not going to go through the derivation of this. It's beyond the scope of the class. But the formula for light is F observer is the square root of 1 minus V over C, where C is the speed of light, divided by 1 plus V over C times the frequency of the source, right? And this is the relative velocity between the listener and the source. Okay. This is, for example, a useful way to detect exoplanets. If there's a planet of sufficient mass orbiting a star, we look at the starlight, and as the planet orbits, the star will also wobble because the two are really orbiting around their combined center of mass. We'll see the starlight red shifted. That means shifted to lower frequencies when the star is moving away. And then blue shifted, shifted to higher frequencies when the star is moving towards us. Timing up those changes between red shift and blue shift can tell us about the orbiting companion orbiting a star. Okay. So what happens as you approach or break the speed of waves? The source moves faster than waves in a particular medium. There's a couple of examples of this. The most common one that people go to is a sonic boom, when a jet breaks the sound barrier. But a more familiar example is a ski boat on a lake. The speed of waves on a lake is something like 1 meter per second, about walking speed. And as a boat goes by faster than walking speed, you see a shock front. And a shock front is lines that are tangent to the circles of outgoing waves from those points. Okay, so those tangent lines create a triangle. For a boat on a lake, you call that a boat wake. We also see this wake or bow shock in stars moving through gases, and for example in the Orion Nebula in the picture over on the right. So as you go faster than the sound barrier, this wake angle becomes smaller the faster you go relative to the speed of sound or whatever wave you're talking about. So the ratio, the velocity of the source of the waves divided by the velocity of waves themselves is called the Mach number. And there's the angle of the wake. Mach angle is sine of theta, right? So theta is inverse sine of the velocity of the waves divided by the velocity of the source. All right, so that concludes our lecture for today and for the week. And I'll try to produce another lecture when we start electricity and magnetism next week. Have a good week. Thanks.